Okay, so you should have done your warm-up. And let's just go over the answers here. Sorry about that. Alright, so the mean of the sampling distribution, so the mean of p hat is equal to p. So you're just going to take that 72.3% to get 0.723. The standard deviation, so there's your formula. Plug everything in, you get 0.0448. Again, this formula, check to see if the 10% condition is met. So this formula is only accurate if that 10% condition has been met. They don't tell us how many flights, but we can assume that there's at least 1,000 American Airlines flights. That's reasonable to assume. The normal condition, so you want to check your n times p and then n times 1 minus p. Both of those numbers are at least 10, so that means our sampling distribution of p hat is approximately normal. It doesn't mean that p is normal or, it just means the sampling distribution of p hat is approximately normal. So then here, when you go to plug everything in, you're trying to, it's a normal with this mean, the standard deviation. You're trying to find the probability that p hat is greater than 0.68, so you can use the normal CDF. Again, you can convert that to a z-score if you want, use your chart. In a sample of 100 flights, there is a 0.8317 chance of observing an on-time percent of 68% or more. Okay? Alright, the homework answers you can check on your own, and if you have any questions about anything, you can email me. To get to the lessons, the first thing we're going to start with here is we're going to start with this worksheet that says the sampling distribution and central limit theorem investigation. So you are going to go to this website and pretty much follow the instructions here. So I have that website up right here. So you want to get to that site there. You want to just follow the instructions. Just go there. I think everything is good. If you get stuck at any, so I'm going to ask that you pause the video and kind of go through this exercise to explore this on your own. Obviously, I'm going to go over it with you, but you're going to learn more if you explore it and do it on your own. So take a second, pause the video, do that. If you get stuck at any point, especially the place where kids get stuck is when they get to the point to answer these questions right here. If you get stuck, you can start to play the video again and then pause it again after the point that you were stuck on, so you can try to explore the concept again on your own, okay? So, sorry, I'm working in a really confined space here, so I'm just got things on the floor and things all over the place, so it takes me a second to go back and forth. Alright, so let's go through this activity. Alright, so when you're here, if you're looking at number 1 in your paper, it says click lower 3. So my lower 3 have been cleared. And select normal from the drop-down menu. The original histogram is your parent population. So this is my original population. This is the population for which I'll be selecting my samples. So my mean right now is 16. My standard deviation is 5. And again, the shape is normal. And I know it's normal. It says it's normal. I don't have to say approximately. I know it's normal. And number 3, what you're asked to do there is you want to make sure you have this n equals 5 there, and it says animated, and you're going to hit that button there. And if you notice there are these 5 little bars drop down, and then there's one blue bar down there. And if I did it again, this is the n equal 5, sorry. I get another blue bar down there. So now I have 2 blue bars. They have a mean of 0, so they're right centered at each other, I guess. Or maybe the means, I think the mean's not the mean calculation's not working. That stinks. Anyways, as I keep doing this, hopefully it'll work when you guys do it. All right, so what each of these black bar represents, each of these black bars is one observation from this data set right here. So it's one data value. So if these were, the mean is 16 here, so maybe this value is 16. These ones are 13 and 13 and 12 and 11. So it's just one data value from this data set. And then these blue bars is the mean. It's the x bars of these 5 values. So when I select another one, I get 5 more values, and they had that x bar. If I did it again, I'd have 5 more values, and they'd have x bar. So what I'm going to do now is I'm going to clear these ones down here, and I'm going to do this more times here. So I'm going to do it for 100,000 samples. Now the mean worked. So if I did it 100,000 times, if you notice here, I got a mean of 15.99, which is, so again, all these blue bars here are my x bars. So I've got a mean of 15.99 of all, so it's a mean of all the x bars, and they have that standard deviation. And again, I'm going to say here it looks bell-shaped or approximately normal. If I clear the lower 3, and instead of doing n equals 5, I'm going to do n equals 20. So when I do n equals 20 now, I'm going to do it again 100,000 times. And if you notice here, I got a mean of 16, which is great because I'm dead on. So this is the mean of all those x bars. And I've got a standard deviation of 1.2. And again, I'm pretty approximately normal. So just like we saw before with the Reese's Pieces and the proportions, you are seeing here that your standard deviation is getting smaller as your sample size is getting larger. Okay? Again, so that takes care of number 6. So then underneath number 6 on the worksheet, it says note. Any statistic you can compute in a sample has a sampling distribution, such as a median, standard deviation, and variance. So if you notice here, we can actually change. You could change it, and you could take sample medians from this. So what would be happening here, sorry, I should animate it one time for you. So that's a sample of 20 medians, and that's the average of those medians. So, sorry, I didn't say that right. This is the sample. This is 20 data values, and that's the median of those 20 data values. I'm going to clear this, and I'm going to switch this back to 5. All right, so then if I do, let's try this again. So these are 5 data values, and that's the median of those 5 data values. Do it again. 5 data values, that's the median of those 5 data values. So you can see that would be the medians of 100,000 samples of size 5. You can have a sampling distribution. If you notice here, it looks like they do a sampling distribution for the standard deviation. So again, there's 5 data values, and they have that standard deviation. 5 more data values, and they have that standard deviation. I could do that many, many times. There's the distribution of the standard deviations. Okay, you don't need to know any of that stuff. The only thing you need to worry about in this class is the mean and the proportion, okay? But that little note there, just realize you can have a sampling distribution for any statistic, so any characteristic that you can measure from your population. Okay, so that bold thing on the back of the worksheet says you should have noticed that the shape of your sampling distribution of the sample mean approaches the normal distribution if the population is normally distributed. So all those x bars that we had were all normally distributed. Now let's look to see the shape if the shape is not normal. So we're going to select skew now from up here. So now I have a skewed distribution. So now my mean, it's a different data set. My mean is 8.08. My standard deviation is 2.79 and, or sorry, 6.22. And I am right skewed. Again, we could do the same thing here. I got samples of size 5. I can select 100,000 there. So when I take samples of size 5, so what I did here, again, the same thing. Like if I do one here, there's a sample of 5 data points, and then they have their own median or their own mean, which gets added to this curve. Here's 5 more data points again. The mean gets added to that curve, the x bar. So this is the distribution of all the x bars. The mean, same as my original mean. My standard deviation is smaller than my original standard deviation, but if you notice there's still a little bit of a right skew. Instead of clearing this graph here, I am actually going to go down here. Oh, it's going to clear it anyways. But I'm going to change this one down here to 20 so you can see both of them. And I'm going to hit that 100. If you notice here, so I've got 8.09, 8.09. So again, these are all these blue bars are X bars given a sample size of size 5. So I take a sample of 5 from here, find the X bar, plot it. Take a sample of size 5, find the X bar, plot it. Take a sample size 20, find the X bar, plot it. Take a sample size 20, find the X bar, plot it. So you can see here, this one still has a little bit of a right skew. This one looks more normal. The standard deviation is much smaller. Both of them have a smaller standard deviation than the original one, but this standard deviation is smaller than this one. So again, as that sample size is increasing, we're seeing our standard deviation become smaller. The last thing at the bottom of that page, it says you should have noticed that the shape of your sampling distribution is of the sample mean approaches the normal distribution, even if the population is not normally distributed. This will be true for skewed distributions, uniform, or any shape you can think of. You can experiment for yourself with this applet. So you can make your own, like you could play around with the uniform one. So this, again here, everything is flat. I still get a nice bell-shaped curve, and the standard deviation still decreases as my sample size gets larger. You can make your own curve. So you just like change it with the mouse. You can make it look however you want. And you can see there again, I can pull X bars from that and I can get a sampling distribution. Okay? All right. Before we go to the notes, again, shuffling of papers because I can't figure out where I put anything. Before we get to the notes, we're gonna watch a little video now. All right.
Funding for this program is provided by Annenberg.
Try to fast forward here to the relevant parts. This will help you understand what's happening though.
Hi, I'm Pardis Betty, and this is Against All Odds, where we make statistics count. Meet the third grade class at Monica Ross School in Ojai, California. 20 rambunctious 9-year-olds who are about to become a living demonstration of how, with the right statistical tools, we can use samples from a population to make inferences about the population as a whole. Remember, we get statistics from sample data, while parameters are generally unknown, because they describe an entire population. Here's our population, the 9-year-olds at Monica Ross, lining up according to their height, 50 inches at one end, 57 inches at the other, with most of them clustered around the center, near 53 or 54 inches. This is our population distribution, the distribution of values in our whole population of 9-year-olds in the class. When we plot this out, you won't be surprised by now to see that the shape of the distribution is approximately a normal curve, from which we can calculate the exact mean mu, 53.4 inches, and the standard deviation sigma, 1.8 inches. Okay, now we're going to take some random samples from our population. Here comes the first sample of 4 students. Throughout this example, we're going to stick with 4 as our sample size. Once again, we calculate the mean. In this case, the sample mean, or X bar, which comes out at 53 inches. Now we take a different random sample of 4. This time, the sample mean is 52.25 inches. From a third random sample, we get an X bar of 52.75 inches. From a fourth, a different distribution, but an X bar that happens to be the same as the last. And from a fifth random sample, we get a sample mean of 53.25 inches. We can keep going until we've selected all possible samples of 4 from our population of 20. And now we can plot out all the sample means we calculated. What we get is a distribution of our sample means, or to put it another way, a sampling distribution of X bar, a distribution of X bar values from all possible samples of size 4. And like any distribution, it can be described by its shape, center, and spread. The shape is our familiar normal curve. The center is the mean of X bar, 53.4 inches, which is exactly what we got for the mean when we calculated it from the population as a whole. But when we directly compare the population distribution to our sampling distribution, we can see that while the center is the same, the spread of the sampling distribution is much less. In fact, sample means are always less variable than individuals. That makes sense. A random sample should include a variety of individuals. From our population, some short, some medium, some tall. The sample mean literally averages out that variety, so we see less variation. There is a precise relationship between the standard deviation of the sample mean and the standard deviation of the individual heights. Here it is. The standard deviation of the sample mean is simply the population standard deviation divided by the square root of the sample size, in our case 4. So the standard deviation of our sample mean is 0.9 inches. Let's see how we can
Okay,
put this fact to use in a situation. So far, we've been talking about population distributions that follow a roughly normal curve. What if we were to take a very different population distribution? The mayor's 24-hour constituent service hotline in Boston answers hundreds of thousands of calls every year. The operators handle everything from simple requests to more complicated questions about city services.
Typically, people call to report things like potholes or streetlights that might be out in their neighborhood.
People put trash out too early, or people have trash out too late, or people aren't keeping their property clean.
They call from some street that in a major 4-lane street where they say there's a turkey running down the middle of the street.
There was one where a skunk got stuck in a revolving door.
I had one recently about a little boy who wanted to request to speak to a park ranger with a horse.
The thing about calls to this and most other call centers is that the length of the calls varies widely.
So the average length of our calls in the 24-hour hotline is about 1.5 minutes, but obviously that can range.
Most calls are relatively brief, but a few can just go on and on. The mayor's hotline answered a total of 21,669 calls in 1 month. If we plot the length of each call, the variable, against the number of calls, we'd get a distribution sharply skewed to the right. You can see it on this density curve, representing the month's call durations. If we sampled from this population, would our sampling distribution also be skewed to the right? You might expect so, so let's find out, using different sample sizes, starting with samples of size 10. Let's take our first sample of size 10. For this sample, the mean length of the calls is 98.7 seconds. We can start to build a histogram using the sample mean. Let's continue taking samples of size 10, each time finding the mean of the sample and adding it to our histogram. This final histogram is based on 40 different samples of size 10. We can do the same thing with 40 different samples of size 20. And finally, we can do it again with 40 different samples with an N of 60. Now let's compare our sampling distributions with the original population distribution for all calls to the mayor's hotline. The spread of all of the sampling distributions is smaller than the spread of the population distribution. And you can see that the spread of the sampling distributions tightens still further as the N increases. Interestingly, while the smallest sample size with an N of 10 is still right skewed, the asymmetry decreases as the sample size gets bigger. By the time N equals 60, we've lost the skew and the sampling distribution of the sample mean looks pretty much normal. The normal quantile plot of X-bar data from 40 samples of size 60 looks like a pretty straight line, underscoring that our data are normal. This happens because with larger samples we are less likely to get all big or all small numbers. We usually get a mix. Some X-bars will be above mu, some below. So we get an approximately normal shape for the sampling distribution, even though the parent population isn't normal. What we've uncovered here is one of the most powerful tools statisticians possess, called the central limit theorem. This states that regardless of the shape of the population distribution, the sampling distribution of the sample mean will be approximately normal if the sample size is large enough. It's because of the central limit theorem that statisticians can generalize from sample data to the larger population. We'll be seeing how that can be useful in later modules about confidence intervals and significance tests. Stay tuned. I'm Party Sabetti for Against All Odds.
Okay, I will try to come back to this video as we're going through our notes. My focus here is terrible. I don't even think that's any better. Maybe if I come a little closer. I suppose that's a little better. Camera's only like on top of my head and I'm about to bonk myself every time. Okay, anyways. I have lots of fun colored pens here too to keep you entertained. Alright, so sampling distribution of X bar. So remember, not talking about p hat like we were when we did the Reese's Pieces. We're talking about X bar. And the couple things. We know X bar can be approximated by a normal curve. We saw in our app and we just saw in the video, if the population was normal, then the sampling distribution of X bar will also be normal. Then she said if the shape was not normal, the population shape, then if n was large, and your book's going to give you a number, the sampling distribution of X bar would be approximately normal. The mean, she told us in the video, of all the X bars is equal to mu. It makes sense. Again, there's a proof of this, but X bar is an unbiased estimator of mu. So if I take a sample of all the students at Fox Chapel Area High School, and I find, if I take a sample of 30 kids, and I find their average height to be 65 inches, that should be a pretty good estimate of what the actual population height is. Alright, the standard deviation. Again, if your sample gets larger, your standard deviation is getting smaller. This is the formula for that. That formula is only correct if your 10% condition has been met. Alright, the book. These formulas right here. The book has a proof for them. It's on page 445. You don't have to know it. You just need to be able to use those two formulas. Those formulas are in the formula sheet, so you don't have to worry about memorizing them. But if you want to understand, this proof involves combining random variables, and kids don't like it as much, so it's not as maybe straightforward as the binomial one that we did the other day. So that's why I kind of don't really go through this one. But again, it's in the book. All right. So again, you've got some population. You take samples, and then you get some X bars. So in the video, she had those students. She had the entire population of students. And then they took samples of size 4, and then they put all those X bars together. They also had the call center data, and she took samples of various sizes, and then you put all those X bars together. So you've got a population, you've got samples that are distributed, and then you put all the X bars together, and you get the sampling distribution of X bar. Remember, X bar is just your sample mean, okay? Okay. Alright, so again, talking about shape here a little bit. If the shape of the sampling distribution of the sample mean, X bar, depends on the shape of the population. So if the population is normally distributed, then the sampling distribution, I should say of X bar, I probably just didn't print on my computer, of X bar has a normal distribution, with this mean and this standard deviation, provided the 10% condition has been met. So it says the GPAs of all students enrolled in a large university that are approximately normal distribution with this mean and this standard deviation. So when I go ahead here to solve this problem, it says find the probability that one student is randomly selected and this is their GPA. This is no different, I don't have any fancy white out here, no different from what we have done in chapter 2, and we've kind of done it again. So we want to find this probability. I know that this is normal because it told me the mean is 3.02 and the standard deviation is 0.029. So here's my 3.02, 2.95, so I'm somewhere down here, 3.11, and I want to find this probability. Normal CDF, if you're going to use your z-score, you're going to have to convert both of those things to the z-score. Look it up in the chart, find the area to the left, find this area to the left, subtract them. Normal CDF, my lower bound is 2.95, upper 3.11, mean 3.02, standard deviation 0.029. I brought a calculator home from school. All right, normal CDF, 2.95, 3.11, 3.02, 0.029. Nope, I did that wrong. Got rid of that one. Okay. So I get 0.2172. So again, here I could say, let's switch colors. Let's brighten up our day here a little bit. This is like a lavender. There is a 21.72% chance one student has a GPA between 2.95 and 3.11. Okay. Again, that's pretty much what we've been doing. Next one says, find the probability that the mean GPA of a random sample of 20 students is between those two numbers. I'm not talking about one kid anymore. One kid. I'm bored. I'm talking about 20 kids, and I'm talking about their mean now. So I want to find this probability. All right, so now I know that the sampling distribution is normal because the population is normal. But my mean of all these is 3.02. This is mean of x bar. My standard deviation of all the x bars is 0.29 divided by the square root of 20. I do that math. Oh, just like at school, there's a glare. Isn't that comforting? Alright, so 0.0648. So over here, I got my normal CDF. And my lower bound, my upper bound, my mean, my new standard deviation, because I'm talking about what's the likelihood that the mean is between these two numbers. I want to compare this back to that sampling distribution that I was talking about. I want to use this distribution to solve this problem, the distribution of all the x bars. For the first problem, I was using this distribution, the distribution of everybody, okay? All right, I plug all that in. I don't know why I did that. That's all the same. All right, so when I get this, it is much more likely in this there. So there is a 77.76% chance of observing a sample mean GPA between 2.95 and 3.11. So it is much more likely that I'm going to observe a sample mean between those numbers than I am going to observe one kid. It's much more likely. This distribution, remember, this is much narrower distribution than this original distribution was. If I take a sample, it's much more likely that the mean is going to be in those values than one kid's going to be between those values. Okay, the essential limit there. Oh, and if you're appreciating my colored printing here, don't get used to it because future videos are going to be black and white with the paper, that is. I still have my fun pens. All right, the central limit theorem. So most population distributions are not normal. What's the shape of the sampling distribution? So basically the idea here is what we just looked at on the app as well as with the call center data in the video. So in this one, if the original population is normal, your sampling distribution is going to be normal only if the sample is large. So when n is large. That's what she said in the video. Kind of could see that a little bit on the applet. What your book is going to say here is that if the population, this is your central limit theorem right here. If the population distribution is not normal, so if my original population is not normal, the call center data in the video, not normal. The central limit theorem tells us that the sampling distribution of X bar will be approximately normal in most cases if n is greater than or equal to 30. Okay? This other one right here, we already just talked about. This one says that the population is normal, so is the sampling distribution. It's true no matter what the sample size is. So in this particular one, for the central limit theorem, because your population distribution is not, I should have bolded that. Okay. All right. So here we are on this page. Go ahead. Try these two problems. Pause the video. Try them on your own. When you're done trying them, unpause the video, and we shall discuss. All right. So this one, first one here says, find the probability that the mean age for a random sample of 36 students would be less than 25 years. So I changed this notation in recent years. So this should read, sorry, I'm reaching into my bag to grab the right pen, but I don't have any whiteouts. But I would prefer now that we write it like this. So normal. This is the sampling distribution of X bar. So mean of X bar, mu of X bar, and then sigma of X bar is 2/3. Okay, so I already wrote it up there, so you don't really need to write it again up there. Just make sure you write the word normal. So then here's my curve. So I want to find the probability that X bar is less than 25. So there's my normal CDF. There's my answer. There's approximately a 6.7% chance of obtaining a sample size of 36 with the sample mean less than 25 years. Okay. If you did what I said, and you paused the video, and you actually attempted this problem on your own, I am about to floor you here, because you probably did it wrong. If you didn't do the problem on your own, then you're totally just missing out on all this excitement right now. All right, so ready for the big reveal? You can't do this problem, people. All right, look. The original population, it says up here, it's skewed to the right. Why could I do this problem? I could do this problem because my sample size was greater than 30. I didn't check the 10% condition here, but I'm assuming it's been met. Okay, I could use the normal distribution to solve this problem because I had a sample size bigger than 30. It didn't matter what the shape of my population is. But down here, if I got a population that's skewed to the right, I can't use the normal distribution to solve the problem. The normal distribution looks like this. If I'm trying to find the probability of somebody being at least 27 years old, the answer I'm going to get from a right skewed distribution is going to be very different from the answer I get from a normal distribution. I can do it up here because I'm talking about the X bars, and the X bars are normally distributed. Down here, I can't do it. It's skewed to the right. I can't find that answer. Okay? Let's see here. Okay, this last page here, this is just, sorry, again, too many papers. Can't keep myself straight right now. Too many papers in a little itty-bitty area. Okay, last page here, summary. Alright, so, okay, X bar, unbiased estimator mu, mean of all the X bars is equal to mu. Standard deviation, again, as long as that 10% condition's been met, standard deviation gets smaller as the sample size gets larger. Central limit theorem says when n is large, in our case it's going to be 30, so the sampling distribution of X bar will be approximately normal in most cases. For you, it'll be all cases, okay? And then if the population is normal, so is the sampling distribution of X bar. All right, those are the practice problems that you want to work on to prepare yourself for your test.